In this highlight video, we're going to talk about the reactions of epoxides. Remember, epoxides are ethers, but they're ethers that are in a three-membered ring. And as we'll talk about in a minute, this arrangement gives epoxides special reactivity. After we've watched this video, you should be able to contrast the reaction pathways of epoxides, particularly the different outcomes of acid-catalyzed ring opening and nucleophilic ring opening. While epoxides are stable, they are found in naturally occurring molecules, they are more reactive than other alkyl ethers. So why do you think that would be? Well, let's look at the two carbons on each side of this oxygen. What would be the hybridization of these carbons? Well, there's no pi bonds, so they should be sp3 hybridized, which would favor bond angles of 109.5 degrees, right? However, we know that if we have to bend these bonds into a three-membered ring, these two bond angles here are in fact going to be only 60 degrees. So this creates a lot of angle strain. And this angle strain increases the reactivity of epoxides. I think of epoxides like a mouse trap. It's strained and pulled back, and if there's given any energy, it just wants to snap open. The epoxides can be induced to snap open in two different ways. One is to protonate the oxygen to make that oxygen a better leaving group. This is the same strategy that we have used for alcohols. These are acid-catalyzed reactions then. The other approach in this case is simply to use a stronger nucleophile. Because there's no acidic proton on the oxygen anymore, we can increase the nucleophilicity and use a basic nucleophile. All right, so we have two different approaches. We could use acidic conditions, or we can use basic conditions. Let's look at two examples of epoxide ring opening under acidic conditions. So just like we've seen before, the first step in an acid-catalyzed reaction is protonation. So in this case, it's the oxygen that's going to be the most basic position, and it can be protonated to make that oxygen be a better leaving group. Notice that this oxygen now has three bonds with a plus charge, which is the same as what we saw for the water molecules that were leaving groups. In the second step, a nucleophile can react with one of the carbons of the epoxide ring. Now this plus charge on the oxygen is also shared with the two carbons adjacent, because this carbon-oxygen bond is kind of stretching open, wanting to break, and that gives some delta plus. So the water can come in from this side, on the opposite side of the oxygen, or it could come in from this side to be on the opposite side of the oxygen. Let's label this as pathway A, and so if we opened it up that way, we would get the new alcohol. This is an SN2 substitution, so the nucleophile comes in from the side opposite of the leaving group, and we get this intermediate. This would be pathway A. If we follow pathway B, the water molecule comes in from the opposite side, again from the side opposite of the epoxide. The bond that's part of the epoxide keeps its same stereochemistry, and we get this intermediate. Now the last two steps here are just deprotonation. And so if we can fit this in, we can use the conjugate base of our acid. To remove one of these protons, just an acid-base step. And we get an alcohol there and an alcohol here. If we do the same thing over here, we remove one of these protons, and we get this product. And this oxygen is back like this. Notice that both of these diols have the alcohols being trans to each other. There and there. So in fact, what's the relationship between these two molecules? Are they the same? No, these two in fact are enantiomers. Alright, so we have started out with, this is an achiral molecule over here, right, because there's a plane of symmetry right down the middle of that. So there's no, well, there are two chirality centers or stereogenic centers, but this would be meso. And we end up with a racemic mixture as our product. Notice that this is an SN2 substitution, so when the nucleophile comes in, it always comes in from the backside to invert the stereochemistry at that center. Once the epoxide is protonated, various nucleophiles can be used to open up the epoxide ring. So let's look at this reaction where we're using HBr. So the first step, just like before, is going to be protonation of the oxygen to make it a better leaving group. To get to this intermediate. Now in our second step, bromide can react with one of the two carbons of the epoxide ring. But notice that in this case, those two carbons are unequally substituted. Right? The one on the top right here is more highly substituted than the one down here because it has an extra methyl group. Now, because this carbon-oxygen bonds are kind of stretching to try to open, the more highly substituted position can hold more partial positive charge. Because remember, more highly substituted carbocations are more stable. So, our nucleophile is then going to come in preferentially from the more highly substituted side. It's going to open up the epoxide ring just like we did before. And so this is going to give us an alcohol on this side, but we're going to be doing an inversion of configuration on the top carbon. It means that because the epoxide ring was going back, the new nucleophile is going to be coming forward. So that was the nucleophile, and the methyl group gets pushed back, and the OH opens up. So notice that the two new groups, this one and this one, again are trans. And so this is in fact product, all right, already right here. So what we could say is that under acidic conditions, the nucleophile will attack at the more substituted carbon. All right, because that's the position right here that has a greater partial positive charge. In both of these cases, though, remember that the reaction, the actual substitution step, is SN2, so we are inverting the stereochemistry. Let's see what happens if we open up that epoxide ring under basic conditions. This is so exciting. So in this case, we have our methoxide, which is our nucleophile, right? And it, in fact, could come in from, again, like on our last example, from the more substituted side or the less substituted side. However, because this is a very strong nucleophile, it wants to react so much, it's going to just react with the most exposed position, and so that's going to be the less substituted end of the epoxide. When it does that, it's also SN2, so the new bond, if that carbon-oxygen bond was going back, the new bond will be coming forward. We've made this ether. Our leaving group was just the oxygen, which is not a very good leaving group, but both because of the ring strain and because of the strength of our nucleophile, it is triggered to open up. So now we've formed, this is called an alkoxide, right? It's a conjugate base of an alcohol. And so if we treat this like in our second step with water, it can simply protonate this alkoxide to give us an alcohol for a product. So notice that our two new groups here are again trans to one another. Right? This is SN2. We get inversion of stereochemistry. Now in this case, so under basic conditions, we see that the nucleophile attacks at the most exposed or at the less substituted carbon. Okay, so this gives us different regioselectivity than what we observed for ring opening under acidic conditions. Let's do one more example. In this reaction, we're using this acetylide anion, and it's very basic, very strong nucleophile, and so it's going to again attack at the less substituted end of the epoxide ring. It's going to open up that epoxide ring. Like this. We get this alkoxide as an intermediate, and we add water, or we could add a weak acid. It would work as well, just to protonate the oxygen. because we want the neutral product. Okay, this is OH. And we have our alkyne. Notice for this one, another important thing is that we have formed this carbon-carbon bond. And remember, as I've said before, reactions that lead to carbon-carbon bond formation are very important in synthesis because we need to build up the molecule from a small molecule into a larger molecule.